Section. Introduction. Let's delve into the complexities of avatar relighting. Our eyes are incredibly sensitive to the appearance of faces, so creating a convincing avatar requires detailed modeling of each part of the head that aligns with the environment. This process needs to be done in real time for applications like video games and telecommunications, which is where the challenge lies. There are three main reasons why real-time relighting of human heads with convincing details is a tough nut to crack. Firstly, human heads are made up of complex and diverse materials, each with unique scattering and reflectance properties. For instance, skin reflects light in complex ways due to its microgeometry and significant subsurface scattering. Hair, with its translucent fiber structure, scatters light out of plane and reflects it multiple times. The eyes, with their multiple layers and highly reflective membranes, add another layer of complexity. There's no one-size-fits-all material representation that can accurately depict all these elements, especially in real time. Secondly, accurately tracking and modeling the underlying geometry and motion is a daunting task. This is because deformations don't always provide enough visual markers to track. Lastly, the need for real-time rendering puts a severe constraint on the design of the algorithm. The more photorealistic the result, the higher the cost of transporting light and tracking motion. Our aim is to create a learning framework that can construct real-time renderable head avatars that accurately depict scattering and reflections under any type of illumination. We use exhaustive measurements from a light stage and physically based rendering methods to generalize to novel illuminations. However, extending these methods to dynamic performance capture and non-skin parts like hair and eyeballs is not straightforward. Moreover, obtaining sufficiently accurate geometry and material parameters is a time-consuming process that requires a lot of manual cleanup. Recent neural relighting approaches have tried to bypass the need for accurate geometry and material modeling by modeling the direct relationship between the input, illumination, and output, outgoing radiance, with neural networks and approximated geometry. Despite some promising results, we've noticed that existing methods fall short due to the insufficient expressiveness of both the geometric and appearance representations. For example, none of the methods achieve all-frequency reflections on hair and eyes, and thin structures like hair strands often end up blurred or clumped into larger blobs, making the hair rendering less than photorealistic. To tackle these issues, we're introducing three key contributions. 1. Drivable avatars based on 3D Gaussians that can be efficiently rendered with intricate geometric details. 2. A relightable appearance model based on learned radiance transfer that supports global light transport and all-frequency reflections in real time. 3. A relightable explicit eye model that allows separate control of gaze from other facial movements and enables all-frequency eye reflections for the first time in a fully data-driven manner. Our geometric representation is based on 3D Gaussians that can be rendered in real time. We use 2D convolutional neural networks to decode 3D Gaussians on a shared UV space for a template head, allowing us to track moving heads with intricate geometric details like hair strands. For appearance, we've developed a relightable appearance model based on learnable radiance transfer. This model preconvolves visibility and global light transport, including multi-bounce and subsurface scattering. We've also introduced a novel parameterization of spherical Gaussians with view-dependent visibility that effectively approximates the combined effects of occlusion, Fresnel, and geometric attenuation. Our relightable Gaussian avatar also incorporates an explicit eye model that enables explicit control of the eyeballs. This model naturally supports relighting of the eyes with all-frequency reflections, which is crucial for photorealism under natural environments. We've evaluated various combinations of geometry and relightable appearance models, and our experiments show that the combination of 3D Gaussians with our relighting appearance model outperforms any other combination. Section Summary. Avatar relighting is challenging because human heads have complex and diverse materials with different scattering and reflectance properties, making it difficult to accurately represent them in real time. Precise tracking of head geometry and motion is also challenging, and the real-time requirement limits algorithmic design. To address these challenges, the authors propose a learning framework that builds real-time renderable head avatars with accurate scattering and reflections, using a combination of 3D Gaussians for geometric representation, a relightable appearance model based on learned radiance transfer, and a relightable explicit eye model. Their experiments show that this combination outperforms other methods. Section. Related work. The study of facial avatar modeling has been ongoing for over 50 years. There are numerous research and tools available that make it easier for artists to create 3D facial models. The development of image-based 3D reconstruction has made it possible to capture 3D faces more accurately and automatically, especially in high-end film production. However, these methods mainly focus on the facial skin area. Specialized solutions are needed to reconstruct and model different parts like teeth, lips, facial hair, eyes, and hair. These parts are challenging to scale for dynamic and complete head avatars. Recently, learning-based methods have been developed to represent human heads without needing precise input geometry. Volumetric representations, in particular, have shown potential in representing both skin and more complex geometric structures like hair. To allow real-time rendering with volumes, several hybrid approaches have been suggested. These approaches divide the space for efficient raymarching using a mixture of volumetric primitives or tetrahedra. Point clouds are also used to model head avatars. However, we've noticed that current shape representations for real-time renderable avatars struggle with modeling extremely thin structures like hair strands. To overcome this, we've improved a state-of-the-art efficient scene representation based on 3D Gaussian splatting for animatable facial avatar modeling. We are the first to enable the modeling of animatable and relightable 3D Gaussians. In the early 2000s, visual production drove research into facial reflectance capture and relighting for integrating actors into virtual environments. Debevec's groundbreaking work showed that one light at a time, OLAT, captures could be used to obtain reflectance properties and relight faces in new illuminations by leveraging the linearity of light transport. Subsequent work extended this method to dynamic relighting and fast acquisition of reflectance maps using spherical gradient illuminations. The collection of larger datasets allowed for estimating reflectance from a single image using neural networks. However, accurate reflectance estimation is typically limited to skin regions because the complex structure of hair and eyes makes inverse rendering intractable. It remains a challenge to photo-realistically model complete human heads due to their highly complex and diverse material and geometric composition. Learning-based relighting approaches attempt to directly learn relightable appearance from a light stage capture, instead of modeling BRDF parameters. While these methods show promising relighting for static and dynamic scenes, they do not support generating novel animations, which is an essential requirement for avatars. Portrait relighting methods also enable relighting under novel illuminations given a single image. However, they cannot produce novel view synthesis or temporally coherent dynamic relighting. Bai proposed a neural rendering method that supports global illumination for animatable facial avatars. To enable real-time rendering with natural environments, they distilled a slow teacher model conditioned with individual point lights into a lightweight student model that can be conditioned with environment maps. This work was later extended to articulated hand modeling, compositional modeling of heads and eyeglasses, and scalable training by eliminating the need for teacher-student distillation. These relightable avatars take lighting information as input, which we found to be the main limiting factor for expressiveness in all-frequency relighting. In contrast, we propose to integrate a target illumination at the output of our neural decoder, improving quality and simplifying the learning pipeline. In computer graphics, rendering a scene with global illumination is a costly process due to iterative path tracing or multiple bounce computations. To enable real-time rendering with global light transport, Sloan proposed to precompute a part of light transport that only depends on intrinsic scene properties, such as geometry and reflectance, and then integrate the precomputed intrinsic factor with an extrinsic illumination at runtime. For fast integration, they utilize spherical harmonics as an angular basis. To overcome the limited frequency band in spherical harmonics, follow-up works introduce wavelets, spherical radial basis functions, spherical Gaussians, anisotropic spherical Gaussians, and neural network-based decompositions. Similarly, neural PRT applies the same principle to screen space relighting based on neural deferred rendering. Despite many desirable properties, these methods primarily focus on static scenes due to the dependency on knowing geometry and material properties. Unfortunately, we neither know the geometry and material properties for human heads a priori, nor are they static. Thus, we propose to learn the intrinsic radiance transfer from dynamic real data observations without explicitly assuming any material types or underlying geometry. The closest to our work in terms of the appearance representation is iNerf, where they learn view-independent spherical harmonics for diffuse and view-conditioned spherical harmonics for specular components from image observations to build a relightable eye model. However, this appearance model suffers from the limited expressiveness of spherical harmonics for specular reflections. Empirically, we find that their proposed model does not generalize well to novel view and light directions. Please refer to Sec. for our analysis. Section Summary. Facial avatar modeling has been a topic of research for many years, with advancements in image-based 3D reconstruction allowing for more precise acquisition of facial features. However, existing shape representations struggle with modeling thin structures like hair strands. Additionally, while there have been developments in relighting methods for facial reflectance capture, they often lack photorealism and do not support generating novel animations. Our proposed method aims to address these limitations by integrating a target illumination into the neural decoder, improving quality and simplifying the learning pipeline. Section. Method. In this section, we'll explain the methods we used in our research. We'll cover how we collected our data, the representations we used for geometry and appearance, our relightable eye model, and our training method. We collected our data using a setup similar to previous studies. We captured high-resolution images from multiple angles using 110 cameras and 460 white LED lights. We asked each participant to perform a variety of facial expressions, sentences, and eye movements. In total, we captured about 144,000 frames for each participant. To ensure diverse lighting conditions and stable facial tracking, we used time-multiplexed illumination. This means we alternated between full-on illumination and lighting with groups of 5 lights. We tracked the participant's face using a coarse mesh and stabilized their head pose using the mode pursuit method. We also estimated the eye gaze for both eyes. We then used this data to train our avatar. Our geometric representation is based on a mixture of 3D anisotropic Gaussians. This allows us to represent varying topologies and thin volumetric structures. We rendered avatars as collections of 3D Gaussians. Each Gaussian is defined by a translation, a rotation matrix, per axis scale factors, an opacity value, and a color. The spatial extent of each Gaussian is defined by its covariance matrix. This representation allows for efficient rendering using the elliptical weighted average (EVA) splatting technique. The final color at each pixel is computed using point-based cumulative volumetric rendering. Unlike previous methods, our goal was to create a 3D avatar that can mimic a person's dynamic facial expressions and be relit under different lighting conditions. To achieve this, we needed a relightable appearance model that can adjust the color of all Gaussians based on the environmental lighting. We also needed to adjust the geometry of all Gaussians based on the person's facial expressions. To animate the avatar, we used a shared UV texture map of a coarse template mesh and decoded their transformation and opacity using 2D convolutional neural networks. We used a conditional variational autoencoder, CVAE, to learn the distribution of facial expressions from the data. We defined our encoder and geometry decoder using the learnable parameters for the encoder and decoder, the total number of Gaussians, and the mean and standard deviation of a normal distribution. We computed the sampled latent vector using the reparameterization trick. We also decoded mesh vertices from the latent vector so we could animate the avatars from a headset or latent space manipulation. We computed the final Gaussian position by adding the interpolated coarse mesh position of the corresponding UV coordinates to the decoded position. We assigned UV coordinates to Gaussians by mapping one Gaussian to each texel in the UV map. This parameterization is similar to the mixture of volumetric primitives, MVP, but there are two key differences. First, 3D Gaussians can be rendered more efficiently using splatting. Second, Gaussians can better recreate thin structures, resulting in a sharper appearance for hair. Section Summary. In this section, the authors describe their data acquisition process, which involves capturing multi-view images of participants performing various facial expressions and motions. They also explain their geometric representation using a mixture of 3D anisotropic Gaussians, which allows for efficient rendering and realistic adaptation of the avatar's appearance under different lighting conditions. The authors further discuss the encoding and decoding of facial movements using convolutional neural networks and a conditional variational autoencoder. Section. Appearance. Learned radiance transfer. We're going to talk about how we've developed a model to accurately represent the appearance of faces, taking into account a variety of light effects. These include the scattering of light within the skin, the reflection of light off the skin and eyes, and the scattering of light on hair. In previous studies, it was found that while a diffuse transfer operator, which is a way of modeling how light is scattered, is a low-pass filter of incident illumination, a specular transfer operator, which models mirror-like reflections, needs to be able to represent all frequency information. To effectively distribute the capacity of our network to each component, we break down the final color of each 3D Gaussian, a mathematical function used in our model, into a view-independent diffuse term and a view-dependent specular term. This means that the final color is the sum of these two terms, where the viewing direction is taken into account for the specular term. Our diffuse term is based on spherical harmonics, a mathematical tool used in our model, and includes global light transport effects such as occlusion, subsurface scattering, and multi-bounce scattering. The diffuse color contribution is calculated by integrating an incident illumination, which is the light that hits the face, with a function that models the radiance transfer, which is how the light is scattered. We represent both functions in the spherical harmonics basis, which allows us to efficiently compute this as a dot product of the coefficient vectors. While diffuse light transport is a low-pass filter that requires only second or third-order spherical harmonics, this is not enough to represent shadows. To enable higher frequency shadows while decoding a manageable number of coefficients that can fit on consumer GPU memory, we propose to decode RGB intrinsic spherical harmonics coefficients up to the third order, and only monochrome intrinsic spherical harmonics coefficients from 4th to 8th order. To achieve sharp, mirror-like reflections, for the view-dependent specular term we use a spherical Gaussian as an angular basis. We propose a normalized, angle-based spherical Gaussian, where the standard deviation of angular decay, the lobe axis, the direction of evaluation, and a normalization factor to preserve the integral of the Gaussian are taken into account. We compute a reflection vector as the lobe axis, where the viewing direction evaluated at the Gaussian center, and a normal direction computed for each Gaussian, and the lobe axis are taken into account. Our final color for the specular term of each 3D Gaussian is defined as a learnable view-dependent visibility term that accounts for Fresnel effects and geometric occlusion integrated within the BRDF lobe. For point lights, we use a Dirac delta function multiplied by a light intensity as the incident light for fast evaluation. This equation can be efficiently evaluated with negligible overhead for all frequency continuous illumination by prefiltering the environment maps. This requires only a single mipmap texture lookup per 3D Gaussian, which is a critical property for real-time relighting with all frequency reflections. Although this formulation works well for surfaces, we use 3D Gaussians to also represent thin fiber-like structures such as hair strands. To support specular reflection of both surfaces and fibers in a unified manner, we propose to learn a view-conditioned surface normal. This way, each 3D Gaussian can flexibly choose its underlying reflection behavior without requiring predefining it a priori. Finally, similar to the geometric decoder, we decode radiance transfer parameters using a view-independent decoder and a view-dependent decoder. The normal residual is added to the barycentric interpolated coarse mesh normal to obtain the final normal. In practice, since the geometric decoder and the view-independent decoder take the same input and produce per Gaussian values, we model them using a single decoder. Section Summary. In this section, the authors propose an appearance model for faces that accurately captures various light transport effects, such as subsurface scattering, specular reflections, and multi-bounced scattering. They decompose the final color of each 3D Gaussian into a view-independent diffuse term and a view-dependent specular term. The diffuse term is based on spherical harmonics and incorporates global light transport effects, while the specular term uses a spherical Gaussian to achieve sharp, mirror-like reflections. Section. Relightable explicit eye model. We've developed a model that can accurately recreate the appearance of eyes under different lighting conditions. This model is based on the geometric representation of eyes proposed by Schwartz. In this model, the eyeball is represented as a combination of two spheres, one for the eyeball itself and the other for the cornea. These spheres are adjusted based on the direction of the gaze. The eyeball is defined by four parameters: the radii of the eyeball and cornea, the distance from the center of the eyeball to the center of the cornea along the optical axis, and the position of the eyeball's center relative to the head. We first optimize these parameters using Schwartz's method, then refine them along with the other parameters of the avatar. We use the same geometric and appearance representations for the eyeballs as we do for the rest of the head. However, we found that we need to make some adjustments to accurately recreate the way light reflects off the cornea. Because the cornea acts like a mirror, the point lights in our capture system create reflections that are very small and intense, often saturating the sensor. The rest of the cornea contributes almost no light. This makes it difficult to accurately model the glints in the eye if we try to optimize the position and surface normal of each Gaussian independently. To solve this problem, we fix the position of the Gaussians on the surface of the eyeball and set their normals to match the surface normals of the eyeball mesh. The iris is only visible through the transparent cornea, which refracts light significantly. To account for this refraction, we use a view-dependent albedo for the eyes. This allows the eye's diffuse color to change based on the input viewpoint. We train our model using multi-view video data of a person lit with known point light patterns. We optimize all the trainable network parameters, the static albedo, and the eyeball parameters using a loss function that includes a KL divergence loss on our encoder outputs, a reconstruction loss on the rendered image and the coarse geometry, and a regularization loss. We also include several regularization terms to prevent the Gaussians in the eye from becoming transparent. We use the Atom optimizer with a learning rate of 0.0005 and train our model on 4 NVIDIA A100 GPS with a batch size of 16 for 200,000 iterations. We tested our model on 6 subjects with a variety of races, genders, and hairstyles. Our tests included around 9,000 frames of conversational expressions and about 100 frames of discussed expressions that the model hadn't seen during training. We also excluded 10 unique frontally biased light patterns from the training. We evaluated our model based on PSNR, SSIM, and LPIPS on images masked with the face region to avoid influence from the background. Section Summary. The authors propose an explicit eye model for high-fidelity eye relighting, which parameterizes eyeballs as a smooth blend of 2 spheres representing the eyeball and cornea. To accurately model eye glints and refraction, modifications are made to the eye decoders, including fixing the position and normals of Gaussians on the eyeball surface and using a view-conditioned albedo. The model is trained using multi-view video data and optimized with a loss function that includes reconstruction, regularization, and scale regularization terms. The model is evaluated on diverse subjects using various metrics such as PSNR, SSIM, and LPIPS. Section. Qualitative results. We've made some fascinating discoveries with our avatar reconstruction model, which we'd like to share with you. Our model can create avatars that adapt to new perspectives, expressions, and lighting conditions, including point lights and high-resolution environment maps. One of the most striking features is the mirror-like reflections in the eyes, which accurately depict the environment without losing any intricate details. Our model is not only drivable but also supports real-time relighting, which means it can be controlled in real time from a headset. Although this wasn't our main objective, our method also estimates intrinsic properties of reflectance, such as color, shape, surface direction, multi-bounce scattering, and shiny components, in a self-supervised way. As a result, our method allows for a 3D consistent and high-fidelity breakdown of these intrinsic properties. We compared our geometric representation with 3 variations: our proposed method, our method without the explicit eye model, EEM, and voxel-based primitives. To ensure a fair comparison, we used the same appearance model and only altered the geometric representation. Our results showed that our geometry, based on 3D Gaussians, can better model skin details and hair strands than voxel-based primitives. Moreover, when our full model is combined with an EEM, it creates convincing eye glints. The Gaussian-based model consistently outperforms in all metrics except for the structural similarity index measure, SSIM, in held-out lights. For the appearance representation, we compared our model with existing relightable appearance representations that support real-time rendering with environment maps. The model presented by Yang, which is a linear neural network that explicitly retains the linearity of light transport, showed superior performance than a previous state-of-the-art method. To assess the effectiveness of our specular reflection model, we also replaced our shiny component with view-dependent spherical harmonics proposed by iNerf. Our appearance representation outperforms existing models in most of the metrics. While the linear model produces the correct overall color, the relighting result is blurry and lacks high-frequency details. This is primarily limited by the bottleneck lighting representation. The view-dependent spherical harmonics in iNerf show more detailed reflections, but its expressiveness is limited due to the use of spherical harmonics for specularity. We also noticed that view-dependent spherical harmonics are more prone to overfitting, resulting in flickering artifacts in animation. In contrast, our approach based on spherical Gaussians is not band-limited and thus achieves high-frequency reflections.